So I'm going to go through the Unit 1.4 handout. The review questions start with a reminder about frequency. So the first review question, if you're looking at the Unit 1.4 handouts, is how many times per second does a 250 hertz wave oscillate? Okay, so the answer is that a 250 hertz wave oscillates or completes one cycle 250 times per second. That is, the times per second or cycles per second is the actual unit of the hertz. So that answer to that one is A. The second part says how much time does it take to complete one cycle. So the time for one cycle, if you're observing at one position and watching something move back and forth over time, time for one cycle is the period t, and that is 1 over the frequency. So that means there's 1 over 250 hertz, which is cycles per second. So that's 1 over 250 seconds. And if you do that out on your calculator, take your calculator and you do 1 and you divide by 250, you get 0.004 seconds, which also could be 4 milliseconds, because milli is moving the decimal place 3 points to the right. Okay. All right, for Roman numeral number 1 about transverse and longitudinal waves, please consult the slides and the videos about those. Okay, number 2 is talking about identifying those. Number 1 there, which of the following is not a transverse wave? And the answer there is C, because sound waves are always longitudinal waves. Longitudinal waves are also called compressional waves. And in longitudinal waves, the different particles are moving back and forth about their equilibrium position, and the wave is traveling in the same direction the particles are moving. That's the definition of the longitudinal wave. Okay, the next part is about wave characteristics, and on page 3 of the handout are definitions for amplitude, period, frequency, and wavelength. I will talk about them and use them as I go through these examples. Number 2, middle C, or C4, on the piano has a frequency of 260 hertz. Okay, so for C4, the fourth C on the piano, the frequency is equal to 260 hertz. For C3, which is an octave below that, the frequency is equal to 130 hertz. And then the question is, how do the wavelengths compare? Okay. So the idea with a wavelength is, if you make a plot as a function of distance, and then the displacement of the wave, and if you do a snapshot in time, okay, then the displacement from equilibrium of the particles might look like that. Okay. And when this is distance here on the horizontal axis, if you take the distance between your peaks, that distance will be one wavelength, which we use the Greek letter lambda for wavelength. Okay, so wavelength equals the distance for one cycle of a wave. Okay. Now, if on this same graph I was going to draw a longer wavelength, then it might look something like this. Okay, and again, the distance between the peaks would be equal to one wavelength of that lower frequency waves have longer wavelength. Okay, so that's a good thing to remember here is lower frequencies have longer wavelengths. Okay, so coming back to our question over here, because the frequency of C3 is less than the frequency of C4, the wavelength of C3 is greater than the wavelength of C4. The way to write it is if frequency decreases, wavelength increases. So those are all kind of that same idea. So now the next part, number 3, is talking about amplitude. The amplitude is related to the amount of energy in the wave. It is the maximum displacement from equilibrium that the parts of the particles in the wave experience. Okay, it is also relates to the energy in the wave. Okay, so I'm now going to draw 2 waves of similar frequency but different amplitudes. Okay. Take that out a little bit more there. Okay, so that would be a low amplitude wave. And then if I want to do one that has the same frequency but a higher wave, it would kind of look like that. Those are actually really bad waves. Let me try again. High amplitude, low amplitude of the same frequency. Okay. The amplitude is this maximum distance from equilibrium. Plugging in here so that it doesn't run out of battery on me. This axis again is the displacement. Maximum displacement is the amplitude. The frequency and the wavelength can be the same. Okay, so amplitude is independent of frequency. You can have quiet, low amplitude sounds on low notes or on high notes. They are not related to each other. Okay, so number 3, going back to answering number 3, which says if you increase the amplitude of a wave, you increase the wavelength, and that is number 3 is false. Oh, so now on to Roman numerals. Wave speed. The wave speed is the distance the wave travels over the time it takes to travel that far. Your car speed is miles per hour, miles being the distance, hours being the time. We will usually use units of meters, which again is the distance divided by seconds, which is time. Okay, so that's general. That's just speed generally. For all, anytime you're talking about a speed, that's what the general definition is. But now, if we want to talk about strings, Waves on strings. Wave speed, which we're going to abbreviate by V because velocity is related to speed. That is, for a string, the square root of the tension of the string divided by the density of the string. And in this regard, for density, we're going to be using the mass of the string divided by the length of the string. So because the tension is in the numerator, it means the wave speed is directly proportional to that, and density is inversely related to that. Sorry. It has a direct relationship with tension and indirect relationship with density. Not exactly proportional, but when one goes up there, it should go up or down accordingly. Okay, so number 4 says, if you increase the tension in the rope, so the tension goes up, this equation here tells us that the wave speed is also going to go up. So that is A. And number 5 says, is the wave speed faster on a heavier rope or a lighter rope of the same length? And it should say same tension. So this is kind of a two-stepper. Okay, so if the heavier rope means if the mass goes up, then that means that the density goes up. But if the density goes up, because that density is in the bottom, the denominator of the wave speed equation, then the wave speed will go down. So because density is in the bottom of this equation right here, if the density increases, the wave speed will go down. So that means that the wave speed will be faster on the lighter string, less massive string. The heavier string has a lower. Okay, so that is it. Okay, so that was strings. This is our equation that you're going to use for wave speed on a string. Very often wave speed on a string will be given as a number, and then you're just saying, well, if tension or density or mass or something changes, what happens to the wave speed? Okay, our next topic is the speed of sound in air. So what is the wave speed of sound as it travels through the air? Okay, for our class, we are going to use 340 meters per second. That's an approximate value. The exact value depends on primarily on temperature, but also on elevation and on humidity, but we're not going to consider those factors for our class. The only time we're going to not talk about the speed of sound in air being 343 is the relationship, the impact of temperature change. Okay, so this is what it is. If the temperature increases, the speed of sound in air will also increase. Okay? It is slightly higher when the air temperature is warmer. So that is number 6. Speed of sound in air increases as temperature increases. That's just saying the same exact thing. And we're going to talk about that more next time because this plays a role in a wave phenomenon called refraction, in which sound waves bend towards regions of lower sound speed. Okay. Number 7 then says, when a pianist strikes several notes at once on the piano, how does the speed of sound in air vary for the different pitches? Okay, so this is a really important idea, okay? Both for the strings and for the air. In both cases, the wave speed depends on the properties of the medium the wave is traveling through. What do I mean by properties of the medium? Okay, so for strings, the wave speed depends on the tension and the density. And for sound and air, the wave speed depends on the temperature and slightly on the humidity and things like that, but we're only going to really be talking about the air, okay? But the wave speed itself only depends on the properties of the medium, okay? So when the pianist strikes several notes at once, back to number 7, the speed of sound in air the different pitches does not vary. It stays the same for all frequencies. And that leads us to the 3rd page and Roman numeral number 4. Okay, Roman numeral number 4 says calculate wavelength of longitudinal waves when given a distance between condensations or rarefactions. Okay, so it comes back to this idea of frequency and wavelength. Okay, so I'm going to do the bold font thing first, okay? So if I have a longitudinal waves with lots of dots, like we saw in class today, there were some places where the dots were more dense and then some where they were less dense. Something like that. Okay, so these where there's more dots bunched up together, okay, these are points of maximum condensation. Okay. And then the other points where the dots are farther apart from each other, those would be maximum, what we call rarefaction. Rarefaction. Okay, so then if we were to plot this as a function of distance and distance of the wave, we've got a snapshot in time, and then we have the displacement here from their equilibrium position. Each one of these little dots, okay, is been moved, is varying around its equilibrium position. Okay? So right there, it might be at equilibrium, but then over time, it's going to vary back and forth like that. Okay? When they're all bunched together, that's the max condensation. When they're all farther apart, that's maximum rarefaction. Okay? And so then what that looks like for one of those dots, or sorry, a line, if we just take a line like through there, say we took a line right through here, and we looked as a function of distance, what would be the rarefactions and the condensations? The wavelength is the distance between maximum condensations. I have different scales going on here in my different pictures. Okay. So you can do from peak to peak or trough to trough, max condensation to max condensation, or max rarefaction to max rarefaction. And that will give you the wavelength of a longitudinal wave. Okay. Now the other idea goes back to this idea of wave speed. And the equation that's on the top of this page is that V is equal to F lambda. Does this mean that the wave speed is determined by the frequency and the wavelength? No, okay? What this means is that the relationship between F and lambda, frequency and wavelength, is determined by the wave speed and the wave speed itself, if you remember back up here, is dependent on the properties of the medium. Okay. So this is the compact way to write it. Okay, but the way we will use it is we will find the frequency using a wave speed and a wavelength, or we will find a wavelength using a wave speed and a frequency. Okay, so this is compact, but what it really means if we know wavelength and wave speed, we can get frequency. If we know wave speed and frequency, we can get wavelength. Okay. All right. So number 8 says, if you increase the tension in the string, okay, so tension is going to go up and frequency is going to stay the same. And what we're asked to find is what happens to the wavelength. Okay. So let's take it this way. If tension increases, what does that do? If tension increases, then the wave speed, which equals the square root of the tension over the density, if tension increases, that wave speed will increase. And then if frequency stays the same, then if we use the relationship for lambda up here, lambda is V over F. If F stays the same and V increases, okay, then lambda will increase, which is true. So number 8 is true. Okay, so kind of 2 steps there. The tension changes the wave speed. If the frequency is the same, then the wavelength will be longer, will increase. Okay, and then number 9 is saying the speed of sound in air is 340 meters per second. What is the wavelength in air of middle C? So that's our question mark. And back on the bottom of the first page, we were told that the frequency for middle C, C4, was approximately 260 hertz. So we will combine those in our equation that lambda is V, the wave speed, over F. So that will be 340 meters per second divided by 260 hertz, which is per second. And that will give us 17 divided by 13 meters. Dividing by 20, just reducing the fraction. But in practice, and on your homework and tests, you will just do a division. You will say 340 divided by 260. And that will give you a lambda equal to 1.3 meters. All right, well, hopefully these different wave terminologies will help. And we'll are going to use these ideas, especially frequency, wavelength, period, amplitude, wave speed throughout our whole class. So hopefully that was helpful. Good luck.